So this project, which was initiated in HSS while Cesar Donato was a fellow there, with Dr. Ellis and Dr. Dulan. There was a lot of work involved at the beginning to decide how basically the artificial intelligence was going to work, how it was going to look at the bones, and also which measurements we wanted out of there, because we don't all agree on what we should measure and what the frame of reference is and all those sorts of things. So it involved quite a lot of brainstorming and maths. But anyway, I think we came up with something rather interesting. I had the opportunity to travel to HSS for a full week doing some of the work with Cesar, and eventually Dr. Benasconi, who's here, participated too. The definition of this M1, M2 automatic measurer is an automated process. So it's fully automatic. You don't need to set landmarks. You don't need to tell the computer, for example, that's the area we're looking at, or we don't need to tell the computer this is the first metatarsal head, and then now you can derive the rest of the calculation and find the rest of the bone, for example. It's fully automatic. It's quite fast, but of course it's all based on calculation, so it's going to get even faster. So the whole process takes about 20 seconds. What we've chosen to do is to produce a measurement which is similar to what we already know. It's very difficult to see in 3D, and we can all relate to that. Some people can draw a square pretty well. We can all do that, but not everybody can draw a cube. It's something that, if you have a nice 3D visual ability, you can do it. If you don't, it's more difficult. So we didn't want to change how we think about hallux valgus, but of course these are developments that will come in the future. So we produced an angle, which is the M1, M2 intermetatarsal angle, and there are two ways to present it. It's either the 3D angle, as it is in space, in the 3D space, but we also produce the 2D angle, which is the projection of the 3D angle on the ground plane. Because this is exactly how conventional radiography works. It's a projected X-ray that will show us where the projection of the first and second metals are on the ground plane. So we basically produce the 3D angle, which is the real angle, and its projection on the ground plane, so that we as surgeons can relate to something we know. And also, incidentally, that we can compare it with previous technology in order to validate its clinical use. The process is first to identify clusters of voxels. So basically what the machine does is that it looks at the skeleton and identify areas where basically dark or dense voxels are more frequent. And then from this information, it derives the central axis of each bones. So you can understand also why we started off with the M1, M2 angle. It's because it's easier to do that on a long bone than on a complicated bone like the calcaneus. So the angles show on the 3D rendering view and on the projected digitally reconstructed radiographs. So if you really want to relate to what you know and what you're used to, you're looking at the radiographs, the 2D radiographs. So the advantage is that it really helps with hallux valgus. It doesn't tell us what the rotation of the first metatarsal is, but it's definitely a future development. It's only a case now of teaching the algorithm with more data sets, more information, and it becomes more efficient as time goes on. I think this is key for the development of weight-bearing CT, because what holds us back a little bit is that we all have the intuition this is a great technology, but it gives us so much information that it takes time. And you have the patient with you in your office and you have to give him an answer. It takes you more time to analyze this 3D data. So this will really help us, because it will take the burden off us to have to think about how to measure in 3D. It will be done automatically. And this is the first angle that we chose to tackle because it's the one we use every day. I mean, I don't know for you guys, but half of my practice is bunions, and then the other half is more sexy stuff, but or unusual stuff. But once we've mastered automatic segmentation, we have all the bones and maybe in the future all the tissues, or there's no limit to what we can do and to what we can measure. So now that the algorithm works for this angle, it's going to work for anything that anyone wants to have a look at. It's just a question of time, and it's just a question for the technology to be widespread enough to feed back data sets into the machine learning loop.